Okay, so second day of 3-1, this is going to be some of the same stuff. So we started, what we were doing yesterday is we were doing tangent lines and slopes and things like that. So we defined the slope of a curve where x equals a. So remember, that could be anything. So the slope ended up being f of a plus h minus f of a, and then it ended up being like over a plus h minus a. Remember, every time it just ended up being an h in the denominator. So this is how we find the slope from a to a point incredibly close to a, and that ends up telling us exactly what our slope is going to be. So what we do with this is we want to find the limit of this thing as h approaches 0. So let's sneak in here the limit as h approaches 0. So when this limit actually exists, this limit is called the derivative. And so what we write, our shorthand notation, is we write f with a little like apostrophe and then a. So we read this as f prime of a. Anytime you see that little apostrophe, it's read as prime. So that is our limit definition of a derivative. We've got this 4-step process, and we talked about this when we were doing difference quotients with the review at the very beginning of the year. The first thing is we want to find just this piece. So we kind of break it down. So find f of a plus h first. That's all you do. Then we finish off the numerator. So at this point, now this is very important, at this point all terms must have a factor of h before you go on to step 3. So that part is very, very, very important, because then what happens is, as you can see, the next thing we do is we divide by h, and that gets simplified down. So divide what you've got so far by h and simplify. And then the last thing that comes into play, so now you've got this whole thing simplified down, the last thing is you take the limit as h approaches 0. Take the limit as h approaches 0, and at that point you should be able to just do direct substitution. You should be able to plug the h equals 0 right in. So we're going to look at this first example, find the 4-step process of a derivative. So f of 1, remember we're looking at, f prime of 1, we're looking from 1 to 1 plus h, same thing as we did up above. So first we want to find f of 1 plus h. So this is step 1 in our 4-step derivative process. Just kind of fine-tuning what we were doing with the last lesson. So just like the stuff yesterday, please keep in mind that you don't just square both these terms. You actually write it out twice and FOIL it. And then here I can distribute. And then I would distribute the 3 to both of these terms. So I'd have 3 times 1, and then plus the 2 that's over here, so that ends up being 5. And then 3 times 2h, so that's 6h. And then I've got an 8h right here, and then 3 times h squared. So that's what I get when I simplify that piece of it down. Then step 2 is I do f of 1 plus h and then minus f of 1. So the piece that I already have, then I subtract f of 1, which is 3 times 1 squared plus 2 times 1. So you see this is 5, and then we're subtracting 5, so those pieces cancel out. This is just 8h plus 3h squared. So the part that I wrote up above in step 2, the very important piece, all terms must have a factor of h here. Here I've got 2 different terms, term 1, term 2. They both are a factor of h. I'm sorry, they're both a multiple of h, so they have a factor of h. So step 3, you take what I left off with in step 2, and you divide it by h. So that gives us 8 plus 3h, so we're just about done. The last thing you do is you take the limit of that expression as h approaches 0. Okay, so of course at that point you are free to just directly substitute in the 0 for h, and you end up with a value of 8. So what that means is that if we are looking at this equation right here, at 1, the slope would be about 8. So just for a couple of these, we'll look just so that I can show you. So if we go to graph this, we can plug in the 3x squared plus 2x. And just to show you, so at 1, like right around here, if you find the point way up there, definitely a steep positive slope. You know what I mean? It's hard to say like if it's 8 or 9 exactly, but just to kind of give you an idea of exactly what we're talking about. As the parabola moves through, it's got a pretty steep negative slope, still negative, but headed towards 0. Right at the bottom there, that's a slope of 0. And then it turns positive and it gets bigger and bigger because it gets steeper as it goes throughout the parabola. So just to give you an idea. Next one, example 2. We've now got a different function here. We're finding f prime of 4, which means we're doing this formula up here using 4 plus h and then minus f of 4. So step 1 in our 4-step process is to find f of 4 plus h. So really all we're doing with that is we're just plugging the 4 plus h into the square root. There's not really anything else that can be done in that step. Then 2 is we take that and then we subtract f of 4, which when I plug 4 in here I get 2. So this one's definitely a little bit complicated because I'm supposed to end up with something that has an h in every single factor. So this is going to feel very strange, and this one is very strange. But anytime you're dealing with square roots like this, which is something to keep in mind for your homework, what you do is you multiply this top and bottom by the conjugate. So you multiply by like a rational expression that's the conjugate on top and bottom. So you will see how this ends up playing out. So I'm going to multiply top and bottom by the conjugate. So you can think of this as being like over 1 if you want to. So really all I'm doing is I'm multiplying by an incredibly fancy 1 here, and I'm going to multiply it out. So I take root 4 plus h times root 4 plus h. That just gives me a 4 plus h. And then because I chose the conjugate, my outside and inside terms will cancel out. I would have a plus 2 root 4 plus h minus 2 root 4 plus h. Those would cancel. And then finally I have a negative 2 times a positive 2, which is a negative 4. And then in the denominator, I just have this nice little value, of course, times 1, which doesn't change anything. So what happens here, and this is why I chose that method that I did, the 4's will cancel out, and so all I have is an h in the numerator. So let me rewrite that just so I can talk about it. So now my rules up here say all terms must have a factor of h. This is what confuses people. This is only one term. This is a single monomial. It's got a numerator and a pretty complicated denominator, but it's only one term, and that one term does have a factor of h. So for step 3, I divide by h. Since I'm dealing with a fraction, I'm going to multiply by 1 over h, which of course is the exact same thing. So I multiply by 1 over h, and we know these h's are going to cancel. So I end up with 1 over the square root of 4 plus h plus 2. And what this represents is the slope between 4 and 4 plus h for any value of h that I choose. But of course, I just want the slope at 4, so I want that little teeny tiny h to shrink down to 0. So the last step that I take is I take the limit of this expression as x approaches 0. And just like with the last one, all of this algebraic manipulation should have gotten us to a point where I can just plug the 0 right in. So if I replace the h with a 0, this is just the square root of 4. Of course, the square root of 4 is 2, and 2 plus 2 in the denominator gives me 1/4. So 1/4 is a positive but not very steep denominator. So let me trade out these functions. So instead, I'm going to plug in just the square root of x, which is what that problem was dealing with. So for x equals 4, if we move out, here's 1, 2, 3, 4, right about there, you can see, I mean, my slope is definitely positive, but it's not very steep at all. That seems like it could be a slope of about 1/4. So what do some different derivatives look like? I know that seems like a very vague, weird thing to ask, but I just wanted to show you a couple of important things. So let's say we've got a little coordinate system here. So just draw, I want your graph to look something like that. All right, so 4 important things that we're going to look at. So we've got a curve, comes to a point, and then a straight line is what you should have. So right here, kind of like this little region of the graph, we're going to write that f prime of x is less than 0. So remember, f prime represents the derivative. So I'm in this downward part of the curve. Anywhere in here, the derivative is negative. It's changing. Like it's getting less and less steep, but the derivative is negative throughout that entire part. And then here's an important piece that we need. Right down there at the bottom, when the graph stops decreasing and starts increasing, just for a moment down there, the slope is 0. So that's a very important thing to look at. You would have a horizontal tangent line, because if anything ran tangent to the curve right at that point, it would be horizontal. And then here, where I start to increase, my derivative is positive. Here, this is something that we will spend more time talking about in the next lesson, but here the derivative is actually non-existent. That's an undefined derivative, and that's because if you flip back over to the first page, we defined the slope, the derivative, as a limit. The limit of this weird quotient here. So what happens is, let's say I approach this point from the left-hand side, it looks like my derivative is going to be positive because this is a positive slope over here. But let's say I approach this point from the left-hand side, it appears that my slope is going to be negative. So as I approach from two different sides, the two slopes don't agree with each other, so the limit does not exist. So f prime of x, we could either say it's undefined, we could say it does not exist. We usually say it's undefined, and like I said, we'll talk more about that in the next lesson. And then this over here, f prime of x is constant. That's just part of a linear function, or it should be if I drew it perfectly, but that's just a constant slope. You know, it might be a slope of like -1 or -2 the whole time, whereas these are constantly changing and getting steeper as I go from left to right. All right, so different types of derivatives that we can talk about. So now I say we could with the last lesson, but we're going to write it down anyways. So start with my original point slope form, and then I'm going to start to kind of plug things in here. So this is just the generic point slope form that we've been talking about. We're talking about this point A and then comma f of A. If A is the x value, then f of A would be the y value, and you get that by just plugging A into your function f. So the tangent line we're going to talk about, the y value in question is f of A. So if they ever don't hand you the y value, it's very easy to find. You just plug it into the original function. And then equals the slope is f prime of A. That's our new notation. That's the derivative. So that's going to be the slope at a certain point. And then times the quantity x minus A. So this is our new definition of the tangent line. I just wrote the one up above so you can kind of see where each piece comes from. Okay, next one. We dealt with this function once with the last lesson. We've got this simple rational expression 1 over x. We're going to use the definition of the derivative to find the slope at 2 and then find the equation of a tangent line. So first piece, we want to find f of 2 plus h. So this one, again, very easy. I just replace the denominator with a 2 plus h. There's not really anything I can do beyond that point. Then next, I take that piece that I just found, and then I subtract the function value at 2, which of course would just be 1 over 2. Now this is the part. If we flip back to our rules, after step 2, all terms must have a factor of h. So we've dealt with the rational ones before. What we do is we get a common denominator. So here I multiply by 2 over 2. Here I multiply by 2 plus h over 2 plus h. So I will get 2 over, and then my common denominator will be 4 plus 2h if I distribute the 2. And then minus 2 plus h is now in this numerator over my new common denominator of 2 plus h. So now they have the same denominator, so I can subtract, make sure with that one, the reason I'm drawing parentheses is so that you subtract both of those terms. You need to be careful. So 2 minus 2, those will cancel, but I have a negative h in the numerator. And then I've got my common denominator of 4 plus 2h. So just like we were talking about with that other one, this is technically just one term, one expression, and it does have a factor of h right here in the numerator. So my third thing is to divide by h, but of course, just like the example on the last page, instead of dividing, I'm going to multiply by 1 over h, and the h's will cancel out. So I get negative 1 over 4 plus 3h. So again, what this represents is the slope from 2 to 2 plus h for whatever h is. H could be 0.1, h could be 0.000001. Regardless, this expression is the slope of this function from 2 to 2 plus h. So we want the h to shrink down because we want it to be that like 2.0000001 so that you can't even tell it's a secant line. It essentially just looks like a tangent line. That's what we're going for here. So the fourth part to finding the slope is to take the limit as h approaches 0 of this expression that we just worked so hard to simplify down. So just like all the previous examples, you can just plug that 0 right in here. Plug in a 0, that term goes away, we end up with negative 1 over 4. So that's our slope. Actually, shouldn't have boxed that up because we want a tangent line. If we plug in, we've got up here, we got y minus, we don't have the y value yet, so you need to plug in the y value at 2, which I guess technically we did come up with it right here. We subtracted the y value at 2. So when x equals 2, the function value is 1 over 2. So we've got y minus 1 over 2 equals, we just found the value of the slope was a negative 1/4, and then times x minus the x value, which is 2. So that is what I should box up. That is our tangent line. So let me show you, I want to show you the original graph, and then I want to plot the tangent line on the same exact axes. So here's the original graph. This is 1 over x. Again, this is a graph that we're hopefully comfortable with. I'm going to plot this, so I need to start with the negative 1/4 and then times the quantity x minus 2. To get y by itself, I'm just going to add this 1/2 to both sides, so plus 1/2. Okay, so when I graph this, the tangent line should run, connect with the 2, and then it kind of skims along the surface. So I'm going to zoom in a little bit right where the 2 is. So 2 is right about here. So I'm going to zoom in once, I'll zoom in twice just so you guys can see that. So the point that we're looking at here, 2 is right around there. So the first big thing with a tangent line is that the tangent line connects with the original function right at the point that we're talking about. So right at x equals 2, those intersect. They've got the exact same value. So let me show you. So right around there. And then the whole point is, as we kind of zoom in on 2, you can see that right what that slope would be matches the slope of that tangent line. And of course, as we go off to the left, the curve starts curving back and forth, but right around that point, that's pretty much a straight line. Now let me show you, if we continue to zoom right into that point, we can get ourselves so close that we can't tell the difference between the original function and the tangent. So can you see this big chunk right here? Our green line, the original graph, 1 over x, essentially looks like a straight line, and we could keep getting closer and closer and closer. This isn't even that. There we go. So if I zoomed one more time, those two lines would totally blend together. And this is like half a unit wide that I'm looking at. All right, so another one pretty similar to this. So we've got this original function. We want to use the definition to find the derivative at 0, and then find the tangent line. So start with f of 0 plus h. That's just going to be f of h. So that would be the square root of 1 plus h. And then I'm going to kind of jump in here, save a little space. I take what I started with there, and I subtract f of 0. So if I plug 0 in here, I get the square root of 1 plus 0, which of course is just 1. So that's my original. Now remember, after step 2, everything has to have a factor of h. So I'm going to do exactly what I did on the previous page, where I did that weird conjugate move. So I'm just multiplying by an incredibly fancy 1. Don't let it freak you out. You can think of this as over 1 if it helps you. I'm doing it so that I can get it into one term that has an h in the numerator. So when I multiply these, FOIL these out, root 1 plus h times root 1 plus h is just the quantity 1 plus h. Just like on the previous page, my outside and inside terms will cancel out, and I'll be left with negative 1 times positive 1, which of course is negative 1. And then over the square root of 1 plus h plus 1. So here, my positive 1 and negative 1 will cancel out. So now I have just one term, and it does have a factor of h right there. So step 3 is to divide by h. But again, since a rational expression, I'm going to multiply by 1 over h, and they will cancel. So I get 1 over the square root of 1 plus h, and then plus 1. So again, this thing, it represents the derivative of this graph from 0 to 0 plus h, or from 0 to h. And of course, we want h to be as small as possible. So that's our fourth step, is we take the limit of this expression that we just came up with, as h approaches 0, and we can just plug the 0 right in. So when you plug 0 in here, this becomes the square root of 1, which is 1, so we've got 1 plus 2 in the denominator, and that gives us a slope of 1/2. So that's just part of it here. We want to take a look at what the actual tangent line is, and then we're going to do what we just did on the graph and graph them both at the same time. So tangent line, y minus the y value is what you find in this step right here. That's what you get when you plug 0 into the function. So the y value is 1 equals, then I've got the slope, and then times, I have x minus 0 in parentheses. You can leave it like that. You can, just write it as x. Doesn't really matter. So let's plot these graphs. So we start with the original graph, square root of 1 plus, of course, x for us, because we don't ever use t. So there's a square root function. All it does is it moves us over 1 unit to the left from the normal square root function. And then we can plot our tangent line. So we have 1/2 x. The minus 0, remember, doesn't do a thing, and I can add 1 to the other side. So this is just a nice, simple function. So this is supposed to be the tangent line at x equals 1, so you can see right here. I'm sorry, at x equals 0. So you can see right there the tangent line connects to the original function. They share the same slope, even just for an instant. So we want to get a good graph of what that's going to look like. So between -1 and 1. So from -1 to 1, our square root function, it's all above the x-axis. So if we call this -1, call that +1, and so we know that they both hit there at 1. So our square root function starts right here, kind of goes like this, and then it continues on, just looking like a square root function. And then our function, our tangent line function, takes on the same slope here, but then of course it's linear, so it'll continue on looking just like a linear function to the left and to the right. So it skims right at that one point. They connected the point 0, 1. It carries on what the slope would be if we zoomed in really, really close. But then, of course, the square root function continues on curving, and the linear function is just straight all the way through. All right, so it looks something like that. This one, you guys will see stuff like this on the multiple choice questions on the AP test. So it's supposed to fit with this formula right here. So like this one is supposed to be the function with a number plus h plugged in. So here you've got the function with a number plus h plugged in. And then this is supposed to be just the function with the number plugged in, and then all over h. So here, f of a plus h, that part is being played by 5 to the 2 plus h, and then f of a is 25. So we can kind of work our way backwards. We're trying to figure out what the function was and then what the value of a is. Well, this piece right here makes finding a easy. So a equals 2. We've got that. And then what function did I plug 2 plus h into? Well, that function would just be 5 to the x. So what this crazy expression is trying to do, it's trying to take the derivative of this function at this point. It's the AP test multiple choice. They love that question. All right, last little bit that we're going to work on here. We're going to do the limit definition of a derivative kind of one more time with these ones and then come up with a general rule. So the derivative of f of x equals 3 when x equals 4. So we're going to go from 4 to 4 plus h. So step 1, we want to find f of 4 plus h. So this function, it's just f of x equals 3. No matter what I plug in for x, I just get 3. So that's it for the first step. For the second step, remember I take what I got in the first step and then I subtract f of 4, f of a, whatever I'm looking for. Now when x equals 4, the function is still 3. So I get 0. So that's my change in y, which should make sense. It's a horizontal line. There's no change in y. So step 3 is to take what I got in step 2 and divide it by h. So when I take 0 and I divide it by h, well, I still get 0. And then step 4, whatever I got, I take the limit as h approaches 0 of 0. So my function 0, keep in mind, is just a horizontal line. And so whenever we've got just a constant in here, remember that's always the answer. So what this tells me, and hopefully we knew this already, the derivative, remember, is just a fancy word for slope. So we were trying to find the slope of this line when x equals 4. Well, this is just a horizontal line. The slope is always 0. So no matter what x value I'm looking at, the slope is going to be 0. So the rule says for f of x equals, let's say just k, a constant k, f prime of a equals 0 for all a. So let me just kind of read that back, make sure it makes sense to you. So if the function is just a constant, a horizontal line, the slope of that function at any value is always just going to be 0, no matter what value you're looking for. Okay, my last one here, linear functions. Again, I think we kind of know where we're going with this, but we're going to do a little mini proof. So step 1, we want x to be -2. So we're going to go from -2 to -2 plus h. So step 1 is to find the function value at -2 plus h. So I plug right into my original function. Where there was an x, I replace it. And so this gives me -14 plus 7h minus 2, which if I combine my like terms, I get -16 plus 7h. So that's the first step. That's what I get when I plug a -2 plus h into my linear function. Then step 2, just like all the others, I take what I got in step 1 and I subtract the function value when x is -2. So if I plug in a -2, I get a -16. So minus a -16, of course that switches to plus a positive, and these two will cancel each other out. And so what I end up with, whoops, somehow this 7 became a 2. It was not magic, just a typo. So that should be a 7. So I end up with a 7h after the 16s cancel each other out. So this is the change in y when we're looking at the numerator of that slope function. And remember, just like all the others, I'm not done with step 2 until I have a factor of h. So step 3, I take my results from step 2, divide it by h. So this gives me 7. And then my fourth step is to take what I ended up with in step 3 and take the limit as h approaches 0. So what this represents is the slope between x equals -2 and x equals -2 plus h. It says the slope between is being represented by a 7. So just like up above, because 7 is a constant, as h goes to 0, the horizontal line just remains 7. So this says the derivative of this function right here, when x equals -2, is 7. Well, I bet you could figure out based on linear functions, the derivative at any point is going to be 7. This is just a slope. 7x minus 2, point slope formula. I'm sorry, slope intercept form. So the rule is for f of x equals mx plus b, so again that is the slope intercept form, f prime of a, so a could be any value that you're looking to find the derivative, it just ends up being m, the slope, for all values of a. So those are your first rules. They're very, very basic ones, some that you probably could have come up with, but a constant's derivative is always 0, and a linear function's derivative is always m. So as we work through, we'll come up with some for like quadratics and cubics and trig functions and all sorts of things, but that's just kind of your intro.